This is the 8th lecture of General Dynamics, Principle of Relativity by Max Planck. This is recorded to celebrate the 8th anniversary of LibriVox. For more information or to volunteer, please visit LibriVox.org. In the lecture of yesterday we saw, by means of examples, that all continuous reversible processes of nature may be represented as consequences of the principles of least action, and that the whole course of such a process is uniquely determined as soon as we know, besides the actions which are exerted upon the system from without, the kinetic potential H is a function of the generalized coordinates and their differential coefficients with respect to time. The determination of this function remains then as a special problem, and we recognize here a rich field for further theories and hypotheses. It is my purpose to discuss with you today an hypothesis which represents a magnificent attempt to establish quite generally the dependency of the kinetic potential H upon the velocities, and which is commonly designated as the principle of relativity. The gist of this principle is: it is in no wise possible to detect the motion of a body relative to empty space. In fact, there is absolutely no physical sense in speaking of such a motion. If therefore two observers move with uniform but different velocities, then each of the two with exactly the same right may assert that with respect to empty space he is at rest, and there are no physical methods of measurement enabling us to decide in favour of one or the other. The principle of relativity in its generalized form is a very recent development. The preparatory steps were taken by H. A. Lorentz. It was first generally formulated by Albert Einstein, and was developed into a finished mathematical system by H. Minkowski. However, traces of it extend quite far back into the past, and therefore it seems desirable first to say something concerning the history of its development. The principle of relativity has been recognized in mechanics since the time of Galileo and Newton. It is contained in the form of the simple equations of motion of a material point, since these contain only the acceleration and not the velocity of the point. If therefore we refer the motion of the point first to the coordinates x, y, z, and again to the coordinates x prime, y prime, z prime of a second system, whose axes are directed parallel to the first, and which moves with velocity nu in the direction of the positive x-axis, x prime equals x minus nu t, y prime equals y, z prime equals z, and the form of the equations of motion is not changed in the slightest. Nothing short of the assumption of the general validity of the relativity principle in mechanics can justify the inclusion by physics of the Copernican cosmical system, since through it the independence of all processes upon the earth of the progressive motion of the earth is secured. If one were obliged to take account of this motion, I should have, for example, to admit that the piece of chalk in my hand possesses an enormous kinetic energy corresponding to a velocity of something like 30 kilometers per second. It was without doubt his conviction of the absolute validity of the principle of relativity which guided Heinrich Hertz in the establishment of his fundamental equations for the electrodynamics of moving bodies. The electrodynamics of Hertz is in fact wholly built upon the principle of relativity. It recognizes no absolute motion with regard to empty space. It speaks only of motions of material bodies relative to one another. In accordance with the theory of Hertz, all electrodynamic processes occur in material bodies. If these move, then the electrodynamic processes occurring therein move with them. To speak of an independent state of motion of a medium outside material bodies, such as the ether, has just as little sense in the theory of Hertz as in the modern theory of relativity. but the theory of Hertz has led to various contradictions with experience. I will refer here to the most important of these. Fizeau brought into parallelism a bundle of rays originating in a light source L by means of a lens and then brought it into focus by means of a second lens upon a screen S. In the path of the parallel light rays between the two lenses he placed a tube system of such sort that a transparent liquid could be passed through it, and in such a manner that in one half, the upper, the light rays would pass in the direction of flow of the liquid, while in the other half, the lower, the light rays would pass in the opposite direction. If now a liquid or gas flow through the tube system with velocity nu, then, in accordance with the theory of Hertz, since light must be a process in the substance, the light waves must be transported with the velocity of the liquid. The velocity of light relative to L and S is therefore in the upper part q sub 0 plus nu and the lower part q sub 0 minus nu, if q sub 0 denote the velocity of light relative to the liquid. The difference of these two velocities, 2 nu, should be observable at S through a corresponding interference of the lower and upper light rays, and quite independently of the nature of the flowing substance. Experiment did not confirm this conclusion. Moreover, it showed in gases generally no trace of the expected action, i.e., light is propagated in a flowing gas in the same manner as in a gas at rest. On the other hand, in the case of liquids an effect was certainly indicated, but notably smaller in amount than demanded by the theory of Hertz. Instead of the expected velocity difference 2 nu, the difference 2 nu times 1 minus 1 over n squared only was observed, where n is the refractive index of the liquid. The factor 1 minus 1 over n squared is called the Fresnel coefficient. There is contained for n equals 1 in this expression the result obtained in the case of gases. It follows from the experiment of Fizeau that, as regards electrodynamic processes in a gas, the motion of the gas is practically immaterial. If therefore one holds that electrodynamic processes require for their propagation a substantial carrier, a special medium, then it must be concluded that this medium, the ether, remains at rest when the gas moves in an arbitrary manner. This interpretation forms the basis of the electrodynamics of Lorentz, involving an absolutely quiescent ether. In accordance with this theory, electrodynamic phenomena have only indirectly to do with the motion of matter. Primarily all electrodynamical actions are propagated in ether at rest. Matter influences this propagation only in a secondary way, so far as it is the cause of exciting in greater or less degree resonant vibrations in its smallest parts by means of the electrodynamic waves passing through it. Now, since the refractive properties of substances are also influenced through the resonant vibrations of its smallest particles, there results from this theory a definite connection between the refractive index and the coefficient of Fresnel, and the connection is, as calculation shows, exactly that demanded by measurements. So far, therefore, the theory of Lorentz is confirmed through experience, and the principle of relativity is divested of its general significance. The principle of relativity was immediately confronted by a new difficulty. The theory of a quiescent ether admits the idea of an absolute velocity of a body, namely the velocity relative to the ether. Therefore, in accordance with this theory, of two observers A and B who are in empty space and who move relatively to each other with the uniform velocity nu, it would be at best possible for one rightly to assert that he is at rest relative to the ether. If we assume, for example, that at the moment at which the two observers meet and an instantaneous optical signal, a flash, is made by each, Then an infinitely thin spherical wave spreads out from the place of its origin in all directions through empty space. If therefore the observer A remain at the centre of the sphere, the observer B will not remain at the centre, and as judged by the observer B, the light in his own direction of motion must travel with the velocity c minus nu more slowly than in the opposite direction with the velocity c plus nu, or then in a perpendicular direction with the velocity square root of quantity c squared minus nu squared. Under suitable conditions, the observer B should be able to detect and measure this sort of effect. This elementary consideration led to the celebrated attempt of Michelson to measure the motion of the earth relative to the ether. A parallel beam of rays proceeding from L falls upon a transparent plane parallel to plate P inclined at 45 degrees, by which it is in part transmitted and in part reflected. The transmitted and reflected beams are brought into interference by reflection from suitable metallic mirrors S1 and S2, which are removed by the same distance L from P. If now the earth with the whole apparatus moves in the direction of PS sub 1 with the velocity nu, then the time which the light needs in order to go from P to S sub 1 and back is L divided by the quantity c minus nu plus L divided by the quantity c plus nu equals 2L divided by c multiplied by the quantity 1 plus nu squared over c squared plus so on and so on close bracket. On the other hand, the time which the light needs in order to pass from P to S sub 2 and back to P again is L divided by the square root of the quantity c squared minus nu squared plus L divided by the square root of the quantity c squared minus nu squared equals 2L divided by c multiplied by the quantity open bracket 1 plus 1 half nu squared divided by c squared plus dot 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 close bracket. If now the whole apparatus be turned through a right angle, a noticeable displacement of the interference bands should result, since the time for the passage over the path PS sub 2 is now longer. No trace was observed of the marked effect to be expected. Now, how will it be possible to bring into line this result, established by repeated tests with all the facilities of modern experimental art? E. Cohn has attempted to find the necessary compensation in a certain influence of the air in which the rays are propagated. But for anyone who bears in mind the great results of the atomic theory of dispersion and who does not renounce the simple explanation which this theory gives for the dependence of the refractive index upon the color without introducing something else in its place, the idea that a moving absolutely transparent medium whose refractive index is absolutely equal to 1 shall yet have a notable influence upon the velocity of propagation of light, as the theory of Cohn demands, is not possible of assumption. For this theory distinguishes essentially a transparent medium whose refractive index is equal to 1 from a perfect vacuum. For the former, the velocity of propagation of light in the direction of the velocity nu of the medium with relation to an observer at rest is q equals c plus nu squared divided by c. For a vacuum, on the other hand, q equals c. In the former medium, Cohn's theory of the Michelson experiment predicts no effect, but on the other hand the Michelson experiment showed give a positive effect in a vacuum. In opposition to E. Cohn, H. A. Lorentz and Fitzgerald ascribe the necessary compensation to a contraction of the whole optical apparatus in the direction of the Earth's motion of the order of magnitude v squared divided by c squared. This assumption allows better of the introduction again of the principle of relativity, but it can first completely satisfy this principle when it appears not as necessary hypothesis made to fit the present special case, but as a consequence of a much more general postulate. We have to thank Albert Einstein for the framing of this postulate and H. Minkowski for its further mathematical development. Above all, the general principle of relativity demands the renunciation of the assumption which led H. A. Lorentz to the framing of his theory of a quiescent ether, the assumption of a substantial carrier of electromagnetic waves. For when such a carrier is present, one must assume a definite velocity of a ponderable body as definable with respect to it, and this is exactly that which is excluded by the relativity principle. Thus the ether drops out of the theory, and with it the possibility of mechanical explanation of electrodynamic processes, i.e. of referring them to motions. The latter difficulty, however, does not signify here so much, since it was already known before that no mechanical theory founded upon the continuous motions of the ether permits of being completely carried through. In place of the so-called free ether, there is now substituted the absolute vacuum, in which electromagnetic energy is independently propagated like ponderable atoms. I believe it follows as a consequence that no physical properties can be consistently ascribed to the absolute vacuum. The dielectric constant and the magnetic permeability of a vacuum have no absolute meaning, only relative. If an electrodynamic process were to occur in a ponderable medium as in a vacuum, then it would have absolutely no sense to distinguish between field strength and induction. In fact, one can ascribe to the vacuum any arbitrary value of the dielectric constant, as is indicated by the various systems of units. But how is it now with regard to the velocity of propagation of light? This is also not to be regarded as a property of the vacuum, but as a property of electromagnetic energy which is present in the vacuum. Where there is no energy, there can exist no velocity of propagation. With the complete elimination of the ether, the opportunity is now present for the framing of the principle of relativity. Obviously, we must, as a simple consideration shows, introduce something radically new. In order that the moving observer B mentioned above shall not see the light signal given by him travelling more slowly in his own direction of motion with the velocity c minus nu than in the opposite direction with the velocity c plus nu, it is necessary that he shall not identify the instant of time at which the light had covered the distance c minus nu in the direction of his own motion with the instant of time at which the light has covered the distance c plus nu in the opposite direction, but that he regard the latter instant of time as later. In other words, the observer B measures time differently from observer A. This is a priori quite permissible, for the relativity principle only demands that neither of the two observers shall come into contradiction with himself. However, the possibility is left open that the specifications of times of both observers may be mutually contradictory. It need scarcely be emphasized that this new conception of the idea of time makes the most serious demands upon the capacity of abstraction and the projective power of the physicist. It surpasses in boldness everything previously suggested in speculative natural phenomenon and even in the philosophical theories of knowledge. Non-Euclidean geometry is child's play in comparison. And moreover, the principle of relativity, unlike non-Euclidean geometry, which only comes seriously into consideration in pure mathematics, undoubtedly possesses a real physical significance. The revolution introduced by this principle into the physical conceptions of the world is only to be compared in extent and depth with that brought about by the introduction of the Copernican system of the universe. Since it is difficult, on account of our habitual notions concerning the idea of absolute time, to protect ourselves without special carefully considered rules against logical mistakes in the necessary processes of thought, we shall adopt the mathematical method of treatment. Let us consider then an electrodynamic process in a pure vacuum. First, from the standpoint of an observer A, secondly from the standpoint of an observer B who moves relatively to observer A with a velocity nu in the direction of the x-axis. Then if A employ the system of reference x, y, z, t, and B the system of reference x prime, y prime, z prime, t prime, our first problem is to find the relations among the primed and unprimed quantities. Above all, it is to be noticed that since both systems of reference, the primed and unprimed, are to be like directed, the equations of transformations between the corresponding quantities in the two systems must be so established that it is possible through a transformation of exactly the same kind to pass from the first system to the second, and conversely from the second back to the first system. It follows immediately from this that the velocity of light c prime in a vacuum for the observer B is exactly the same as that for observer A. Thus, if c prime and c are different, c prime is greater than c. Say it would follow that if one passes from one observer A to another observer B who moves with respect to A with uniform velocity, then he would find the velocity of propagation of light for B greater than that for A. This conclusion must likewise hold quite in general independently of the direction in which B moves with respect to A, because all directions in space are equivalent for the observer A. On the same grounds, in passing from B to A, C must be greater than C prime, for all directions in space for the observer B are now equivalent. Since the two inequalities contradict, therefore C prime must be equal to C. Of course, this important result may be generalized immediately so that the totality of the quantities independent of the motion, such as the velocity of light in a vacuum, the constant of gravitation between the two bodies at rest, every isolated electric charge, and the entropy of any physical system, possess the same values for both observers. On the other hand, this law does not hold for quantities such as energy, volume, temperature, etc. For these quantities depend also on the velocity, and a body which is at rest for A is for B a moving body. We inquire now with regard to the form of the equations of transformation between the unprimed and the primed coordinates. For this purpose let us consider, returning to the previous example, the propagation as it appears in the two observers A and B of an instantaneous signal creating an infinitely thin light wave which at the instant at which the observers meet begins to spread out from the common origin of coordinates. For the observer A the wave travels out as a spherical wave. X squared plus y squared plus z squared minus c squared t squared equals 0. For the second observer B, the same wave also travels as a spherical wave with the same velocity, x prime squared plus y prime squared plus z prime squared minus c squared t prime squared equals 0. For the first observer has no advantage over the second observer. B can exactly with the same right as A assert that he is at rest at the center of the spherical wave, and for B after unit time the wave appears with B in the center and A off center, while its appearance for the observer A after unit time appears with A in the center and B off center. The equations of transformation must therefore fulfill the condition that the two last equations, which represent the same physical process, are compatible with each other, and furthermore the passage from the unprimed to the primed quantities must in no wise be distinguished from the reverse passage from the primed to the unprimed quantities. In order to satisfy these conditions we generalize the equations of transformation set up at the beginning of this lecture for the old mechanical principle of relativity in the following manner. X prime equals kappa times the quantity x minus nu t. Y prime equals lambda y. Z prime equals mu z. T prime equals nu t plus rho times x. Here nu denotes, as formerly, the velocity of the observer B relative to A, and the constants kappa, lambda, mu, nu, and rho are yet to be determined. We must have x equals kappa prime multiplied by the quantity x prime minus nu prime t prime, y equals lambda prime y prime, z equals mu prime z prime, t equals nu prime t prime plus rho prime x prime. It is now easy to see that lambda and lambda prime must both equal 1. For if, for example, lambda be greater than 1, then lambda prime must also be greater than 1, for the two transformations are equivalent with regards to the y-axis. In particular, it is impossible that lambda and lambda prime depend upon the direction of motion of the other observer. But now, since, in accordance with what precedes, lambda equals 1 divided by lambda prime, each of the two inequalities contradict, and therefore lambda equals lambda prime equals 1. Likewise, mu equals mu prime equals 1. The condition for identity of the two spherical waves then demands that the expression x squared plus y squared plus z squared minus c squared t squared become, through the transformations of coordinates identical with the expression x prime squared plus y prime squared plus z prime squared minus c squared t prime squared. And from this the equations of transformations follow without ambiguity. X prime equals kappa times the quantity x minus nu t, y prime equals y, z prime equals z, and t prime equals kappa multiplied by the quantity t minus nu x divided by c squared, wherein kappa equals c divided by the square root of the quantity c squared minus nu squared. Conversely, x equals kappa multiplied by the quantity x prime plus nu t prime, y equals y prime, z equals z prime, and t equals kappa multiplied by the quantity t prime plus vx prime divided by c squared. These equations generally permit the passage from the system of reference of one observer to that of the other, thanks to Lorentz, and the principle of relativity asserts that all processes in nature occur in accordance with the same laws and with the same constants for both observers, thanks to Albert Einstein. Mathematically considered, the equations of transformations correspond to a rotation in the four-dimensional system of reference x, y, z, and time through the imaginary angle arctangent I times nu divided by c. That's from Minkowski. Accordingly, the principle of relativity simply teaches that there is in the four-dimensional system of space and time no special characteristic direction, and any doubts concerning the general validity of the principle are of exactly the same kind as those concerning the existence of the antipodians upon the other side of the earth. We will first make some applications of the principle of relativity to processes we have already treated above. That the result of the Michelson experiment is in agreement with the principle of relativity is immediately evident, for in accordance with the relativity principle, the influence of a uniform motion of the earth upon processes on the earth can under no conditions be detected. We consider now the Fizeau experiment with the flowing liquid. If the velocity of propagation of light in the liquid at rest be again q sub 0, then in accordance with the relativity principle q sub 0 is also the velocity of the propagation of light in the flowing liquid for an observer who moves with the liquid, in case we disregard the dispersion of the liquid, for the color of the light is different for the moving observer. If we call this observer B and the velocity of the liquid as above nu, We may employ immediately the above formulae in the calculation of the velocity of propagation of light in the flowing liquid judged by an observer A at the screen S. We have only to put the derivative dx prime by dt prime equals x prime equals q sub 0 to seek the corresponding value of the derivative dx by dt equals x dot. For this obviously gives the velocity sought. Now it follows directly from the equations of transformations that dx by dt equals x dot, which in turn equals the fraction quantity x dot prime plus nu divided by the quantity 1 plus nu x dot prime divided by c squared. And therefore through appropriate substitution the velocity sought in the upper tube after neglecting the higher powers in nu divided by c and nu divided by q sub 0 is x dot equals the quantity q sub 0 plus nu all divided by 1 plus the fraction nu times q sub 0 divided by c squared equals q naught plus nu times the quantity 1 minus q sub 0 squared divided by c squared close bracket. And the corresponding velocity in the lower tube is q sub 0 minus nu multiplied by the quantity 1 minus the fraction q sub 0 squared divided by c squared close bracket. The difference of the two velocities is 2 times nu multiplied by the quantity 1 minus q sub 0 squared over c squared close bracket, which equals 2 nu multiplied by the quantity 1 minus 1 over n squared close bracket, which is the Fresnel coefficient in agreement with the measurements of Fizeau. The significance of the principle of relativity extends not only to optical and other electrodynamic phenomena, but also to all processes of ordinary mechanics, but the familiar expression 1/2 mq squared for the kinetic energy of a mass point moving with the velocity q is incompatible with this principle. But, on the other hand, since all mechanics as well as the rest of physics is governed by the principle of least action, the significance of the relativity principle extends at bottom only to the particular form which it prescribes for the kinetic potential H, and this form, though I will not stop to prove it, is characterized by the simple law that the expression h times dt for every space element of a physical system is an invariant, so it equals h prime times dt prime. With respect to the passage from one observer A to the other observer B, or, what is the same thing, the expression h divided by the quantity square root of c squared minus q squared is in this passage an invariant equaling h prime divided by the square root of the quantity c squared minus q prime squared. Let us now make some applications of this very general law, first to the dynamics of a single mass point in a vacuum, whose state is determined by its velocity q. Let us call the kinetic potential of the mass point for q equals 0 h naught, and consider now the point at an instant when its velocity is q. For an observer B who moves with the velocity q with respect to the observer A, q prime equals 0 at this instant, and therefore h prime equals h naught. But now, since in general h divided by the square root of the quantity c squared minus q squared equals h prime divided by the quantity square root of c squared minus q prime squared, we have after substitution h equals the square root of two terms, 1 minus the second term being the fraction q squared over c squared, and this square root is multiplied by h naught. This equals the square root again of two terms of 1 minus the second term being the fraction x dot squared plus y dot squared plus z dot squared in the numerator divided by c squared in the denominator, and this square root is multiplied by h sub 0. With this value of h, the Lagrangian equations of motion of the previous lecture are applicable. In accordance with an equation from a previous lecture, the kinetic energy of the mass point amounts to E equals x dot times the partial derivative of h with respect to x dot plus y dot times the partial derivative of h with respect to y dot plus z dot times the partial derivative of h with respect to z dot subtract h equals q times the partial derivative of h with respect to q minus h. And all this equals negative h sub 0 divided by the square root of the quantity 1 minus q squared over c squared. And the momentum 2, g, equals the partial derivative of h with respect to q equals negative q h naught divided by c multiplied by the square root of the quantity c squared minus q squared. G over q is called the transverse mass m sub t, and dg by dq is the longitudinal mass m sub l of the point. Accordingly, m sub t equals negative h naught divided by the product c times the square root of the quantity c squared minus q squared. M sub l equals negative c times h naught divided by the quantity c squared minus q squared, which is raised to the 3 halves. For q equals 0, we have m sub t equals m sub l equals m sub 0, which equals negative h sub 0 over c squared. It is apparent if one replaces in the above expressions the constant h naught by the constant m naught that the momentum is g equals m sub 0 q divided by the quantity square root of 1 minus q squared over c squared. And the transverse mass m sub t equals m naught divided by the square root of the quantity 1 minus q squared over c squared. And the longitudinal mass m sub l equals m naught divided by the quantity 1 minus q squared over c squared, all raised to the power of 3 halves. And finally, that the kinetic energy is E equals m naught c squared divided by the square root of the quantity 1 minus q squared over c squared, which equals m naught c squared plus 1 half m naught q squared plus dot dot dot. The familiar value of ordinary mechanics, 1 half m naught q squared, appears here therefore only as an approximate value. These equations have been experimentally tested and confirmed through measurements of A. H. Bucherer and E. Hupke upon the magnetic deflection of electrons. A further example of the invariance of h times dt will be taken from electrodynamics. Let us consider in any given medium any electromagnetic field. For any volume element V of the medium, the law holds that V times dt is invariant in the passage from the one to the other observer. It follows from this that h divided by V is invariant, i.e. the kinetic potential of a unit volume or the space density of kinetic potential is invariant. Hence the following relation exists. ED minus HB equals E prime D prime minus H prime B prime, wherein E and H denote the field strengths and D and B the corresponding inductions. Obviously, a corresponding law for the space energy density ED plus HB will not hold. A third example is selected from thermodynamics. If we take the velocity q of a moving body, the volume V and the temperature T as independent variables, then, as I have shown in the previous lecture, we shall have for the pressure P and the entropy S the following relations. The partial derivative of the kinetic potential H with respect to volume V equals P, and the partial derivative of H with respect to T temperature equals S entropy.
Now since v divided by the square root of c squared minus q squared is invariant and s likewise invariant, it follows from the invariance of h divided by the square root of c squared minus q squared that p is invariant, and also that t divided by the square root of c squared minus q squared is invariant, and hence that p equals p prime and t divided by the square root of c squared minus q squared equals t prime divided by the square root of c squared minus q prime squared. The two observers A and B would estimate that the pressure of a body is the same, but the temperature of the body is different. A special case of this example is supplied when the body considered furnishes a black body radiation. The black body radiation is the only physical system whose dynamics for quasi-stationary processes is known with absolute accuracy. That the black body radiation possesses inertia was first pointed out by F. Hasenhorl. For black body radiation at rest, the energy E sub 0 equals a times t to the power 4 times v is given by the Stefan-Boltzmann law, and the entropy S naught equals the integral d E naught divided by t equals 4/3 a times t cubed v, and the pressure P naught equals a divided by 3 multiplied by t to the power 4. And therefore, in accordance with the above relations, the kinetic potential is h naught equals a t to the fourth times v all divided by 3. Let us imagine now a black body radiation moving with the velocity q with respect to the observer A, and introduce an observer B who is at rest, q equals 0, with reference to the black body radiation. Then h divided by the square root of c squared minus q squared equals h prime divided by the square root of c squared minus q prime squared equals h prime sub 0 divided by c, wherein h prime sub 0 equals a times t prime to the power 4 times v prime all divided by 3. Taking account of the above general relations between t prime and t, v prime and v, this gives for the moving black body radiation the kinetic potential H equals a times t to the fourth times v divided by 3 times the quantity 1 minus q squared over c squared quantity squared, from which all the remaining thermodynamics quantities, the pressure P, the energy E, the momentum G, the longitudinal and transverse masses M, L, and MT of the moving black body radiation are uniquely determined. Colleagues, ladies and gentlemen, I have arrived at the conclusion of my lectures. I have endeavoured to bring before you in bold outline those characteristic advances in the present system of physics which in my opinion are the most important. Another in my place would perhaps have made another and better choice, and at another time it is quite likely that I myself should have done so. The principle of relativity holds, not only for processes in physics, but also for the physicist himself, in that a fixed system of physics exists in reality only for a given physicist and for a given time. But, as in the theory of relativity, there exists invariance in the system of physics, ideas and laws which retain their meaning for all investigators and for all times, and to discover these invariants is always the real endeavour of physical research. We shall work further in this direction in order to leave behind for our successors, where possible, lasting results. For if, while engaged in body and mind in patient and often modest individual endeavour, one thought strengthens and supports us, it is this, that we in physics work not for the day and not for immediate results, so to speak, but for all eternity. I thank you heartily for the encouragement which you have given me. I thank you no less for the patience with which you have followed my lectures to the end, and I trust that it may be possible for many among you to furnish in the direction indicated much valuable service to our beloved science.
End of the eighth lecture of Max Planck, entitled General Dynamics, Principle of Relativity. Read by Paul King, pjk.scripts.mit.edu/pkj.